All right, we are into solutions, and remember again, a solution is made up of two parts. We have the solute, which is the smaller part, and we have our solvent, which is the larger part. And together they do make a solution. A solution is typically the guys that have that aqueous symbol next to them. And usually the name of the solution is the solute. So as we talked about last time, if you had a sodium chloride solution, sodium chloride would be your solute. Most likely water would be your solvent. As we talked about, it's pretty good solvent for things that are polar or ionic. Again, it's a bad solvent, obviously, for things that are non-polar. You would need more of a non-polar solvent. That's that idea, as we talked about, of like dissolves like. So again, things that use the same type of intermolecular forces that they use with themselves, how they interact basically with themselves, will interact well with each other. And that means that typically soluble things are going to be our ionic and polar, our polar and polar things, are nonpolar and nonpolar things. And insoluble typically is really when you kind of cross over there. So if you go polar to nonpolar, you're going to run into some trouble. So as we talked about, although they may be able to interact with each other for a short period of time, over the long period of time, they're really not going to be able to maintain that interaction, and they really will sort of separate out from each other. We talked about electrolytes as well, and we have strong electrolytes, which basically 100% break apart into ions. None of the whole units are still there. They're very good conductors of electricity because they produce a lot of ions in solution really quickly. We also have weak electrolytes, which you obviously can usually recognize with arrows heading in both directions. These guys actually stay together mostly, but will still produce a few ions. So they'll produce a few. So since they're able to produce some ions, they are still able to conduct electricity, but nowhere near as good as a strong electrolyte will. That's sort of our light bulb example. Strong electrolyte, very bright light bulb goes on. Weak electrolyte, kind of a dim light bulb goes on. Non-electrolyte will dissolve, but will have no ions. So no ions there, and will not conduct electricity because of that. We got into sort of at the end there as well, some concentrations, and the one that we stopped at, I think, was percent mass to mass. And that again is the mass of the solute divided by the mass of the solution times 100%. And again, a reminder that the bottom part here is really important, where people make a lot of mistakes is because of the way these problems are oftentimes written, they will break up sort of the solute mass and the solvent mass. So you do want to make sure that you are adding those together. You want the grams of solute plus the grams of solvent. So you want to make sure you do get those. Super common error that people just kind of go with the solvent and think it's really the mass of the solution. Also, if you did have a percentage of that, so as we talked about, I think last time, if you had a 4.5% by mass solution of sodium chloride, you can definitely turn that into a usable sort of conversion factor. That would mean you have 4.5 grams of sodium chloride and 100 grams of solution. Or you could flip it around and go in 100 grams of solution. You got 4.5 grams of sodium chloride. So as we talked about last time, I think we did one at the end there, the very last example. Remember that if you kind of set things up dimensional analysis way, you don't have to worry about necessarily rearranging equations a lot of times, and it'll kind of take care of the math for you. And a more dimensional analysis approach sometimes is really a good idea. Any questions on any of that stuff we talked about last time? Okay, then we're somewhere. Let's see. So we talked about mass percent. So to continue with our sort of percent concentrations, we also have volume percent. That is sometimes abbreviated, as you see there, percent volume to volume, like percent alcohol and so forth. That's what that is. This is actually the volume of the solute over the volume of solution. So it's kind of like milliliters over milliliters, if you will, usually. And times it by 100. This case, you don't have to be as careful as you do with the mass percent, because a lot of times they will just kind of give you the volume of the solution. So unlike sort of mass percent where they kind of break up the solute and the solvent, a lot of times on this one, they really won't kind of break it up into the solute and the solvent. Not that they couldn't, but in most cases, they probably usually will not. Kind of the same idea. You could also, if you have something that is 4.5% by volume here, sodium chloride, you can, just like we did with the mass to mass percentage, turn it into a conversion factor. In this case, what that would mean is you have 4.5 milliliters of sodium chloride in 100 milliliters of the solution. Again, we keep 100, so all the numbers stay the same. You could also, again, flip it around. So I'll come over here to the right. You could go with 100 milliliters of solution on top and our 4.5 milliliters of sodium chloride. So again, much like the other one, you could kind of turn them into a conversion factor and use it in a dimensional analysis, just kind of assuming you have 100 of it, and it will hopefully work out all right. So in addition to percent mass to mass and percent volume to volume, there's sort of a third percentage type of concentration that we sometimes come across. And that is really the combination of both. That is mass to volume percent. And that is percent M to V. That is kind of like grams over milliliters, kind of like density. Yeah, so it's like grams over milliliters. And that is the grams of the solute over the milliliters of the solution. And just like the other two, if you had a 4.5% mass to volume sodium chloride solution, that would mean you would have, because the top number is grams, 4.5 grams of sodium chloride in 100 milliliters of solution. Or again, you could flip it around and use it as a conversion factor the other way, 100 mils of solution and 4.5 grams of sodium chloride. So these percent concentrations do kind of work the same. It just depends on sort of what you're looking to do. And again, each of them, if you are calculating the answer, usually should end up as a percentage. So you don't have to really worry about the other units. Even though technically these units don't cancel, usually if you're going to give an answer here, you could just go percent M/V and not worry about the grams or the milliliters in terms of the units if you're calculating for it. Questions on that there? So why don't we try one here and see? What is the mass to volume percent of bromine in a solution prepared by taking 12 grams of bromine and enough carbon tetrachloride to make 250 milliliters of solution? Okay, so let's take a look at this one. We're looking for the mass to volume percent. So once again, that is percent mass to volume. That is our mass of our solute divided by the volume of solution times 100%. In this case, our solute is the 12 grams of bromine, as that is what's being dissolved in actually carbon tetrachloride. And we're going to make a volume of the solution of 250 milliliters. So we actually have everything we need. Just got to plug it in there. So 12 grams divided by 250 milliliters times it by 100%. Going to get us 4.8%. And again, you could leave this as mass to volume bromine if you like. And again, you don't have to worry too much about the units canceling out. In this case, you could leave your answer as a percentage. First off, any questions on the calculation? Yes, sir. It is possible that if you're asking, could you be given the solute in some other unit? It is possible that you could. So, I mean, you could be given to it in moles, and you might have to use a molar mass to get grams and stuff like that. Good question. Yeah.
So for the equation, we're always going to be using grams and milliliters. So for every given like I don't know liters, we have to convert that to milliliters. So is there any ever an instance where you can substitute those?
Yeah. So usually it's grams and milliliters. And and if you sort of adjust up to like liters, you might have to adjust up to something like maybe kilograms or something like that. Try to kind of a equal sort of adjustment on that. That way you'll be on the right sort of percentage and sort of that. Yeah. Other questions? All right. This also brings up a good idea of what we were talking about earlier and last time. In this case, we had Br2, which, as you hopefully know, is non-polar. And that is why in this particular case, water was not our solvent, but carbon tetrachloride was. A real quick sketch of carbon tetrachloride without all the dots will look something like this. And that is a symmetrical geometry where everything on the outside is the same, which means that is a non-polar molecule as well. And those two are going to work really well together because they both are going to be using those dispersion forces. So they're going to be very soluble in each other. Again, if you try to do the Br2 with the water, you're going to get some layering happening. They are not going to mix with each other again because water's polar. So again, as we've talked about last time, sometimes people think water is always like the solvent. And again, it is a lot of times the solvent, especially for like ionic and polar things. But again, if you're dealing with something that's non-polar, water again would be a terrible solvent. So it's not always necessarily the solvent of choice. Any questions on that there? All right, let's try this one here. Calculate the grams of KCl and the grams of water in 225 grams of an 8% by mass potassium chloride. I'll spit that out right, I think. Potassium chloride solution. Okay, so let's take a look. Once again, we're dealing with percent mass to mass in this case, which is our grams of solute divided by our grams of solution times 100%. In this particular case here, we are looking for the grams of our solute, which is the KCl. By the way, it's a KCl solution, so I know KCl is the solute. And if I'm looking for the grams of it, then obviously I'm looking for the grams of the solute in this case. The grams of the solution was given to us there, which was 225 grams. And we actually have the percent by mass given to us, which is 8%. So you actually have this, and you could actually plug and chug into that equation if you like. Or again, you could take a more dimensional analysis approach if you don't want to rearrange the equation or really even think about the equation, I suppose. You could take that 8%, and again, that means that I would have 8 grams of KCl and 100 grams of solution. Or again, you could flip it around as we talked about, go with 100 grams of solution is 8 grams of KCl. So I have the grams of solution. So again, if I don't want to think about the equation, I can just take the grams of solution, which would be 225 grams, and just think about it like a dimensional analysis type of problem. Grams are on top of solution, which means I would need the grams on the bottom there to cancel. 100 grams of solution. And again, because I'm doing dimensional analysis, I know the math part of it is multiplying the top and dividing the bottom. So again, I don't have to worry about rearranging the equation wrong or anything like that. 225 times 8 divided by 100. Try that again. 225 times 8 divided by 100, not 10. Probably that would be a little bit better. That's going to give me 18 grams of KCl in this case. And again, that would be obviously the same thing that you would get if you rearrange this equation. You would multiply the grams of solution to the other side and divide by 100%, which is essentially what we just did there in dimensional analysis. First off, any question on that there? That is one part of the question, which is how many grams of the KCl. We also want to know how many grams of water. So remember that the grams of the solution is made up of two things, the grams of the solute plus the grams of the solvent, which in this case, because this is ionic, the solvent most likely is water. So that is what we'll be looking for. That's essentially our water here. That's essentially our KCl. And that is our solution together. So we just solved for that. And we know that the mass of the solution was 225 grams, would equal our 18 grams of KCl plus the grams of water, which is our solvent. Subtracting the 18 to the other side is going to tell us that we have basically here 207 grams of water was added. So 207 grams of water and our 18 grams there of KCl mixed together gives us 225 grams for the solution. Any questions on that there? Question on percent concentrations, mass to mass, volume, volume, mass to volume. Okay, so these are concentrations that we do come across, but I would say probably the most common unit of concentration that we come across is molarity. And molarity we talked a little bit about last time as well, but we'll officially talk about here. Molarity is abbreviated with the big M. That is, again, the most common unit that you probably will come across in most cases. So molarity is the moles of solute per liter of solution. So molarity, big M, moles divided by liter. You could think of this just like the density formula, if you will, because we do solve for all three of those things in problems. So sometimes we're looking for the molarity, sometimes we're looking for moles, and sometimes we are looking for liters. So we do actually solve for all these guys. For example, if we want liters, that is moles divided by molarity. And if we want moles, which is a very common calculation, liters times molarity is how you get there. So all three of those, I would say, are very, very commonly used, especially with solutions and concentrations. Also, a couple of other conversions that we've done previously is used a lot with solutions and molarity, and that is a lot of times you weigh things out in grams and you need to convert those grams to moles. So again, the molar mass from the periodic table is a very common conversion factor that we use to do that to get the top number. Also, as you might know, when you measure things out in terms of volumes, usually you're doing milliliters. So milliliters to liters is a very common conversion that we use a lot with this. And again, there's 1,000 milliliters is 1 liter to kind of get that. If you are using molarity and volume together, like in this fashion, it needs to be in liters. Yeah. Otherwise, if you multiply by milliliters, you are not getting what you think you're getting. You are not getting moles. You're getting what are known as millimoles, which are like moles, but off by a factor of 1,000, basically. So you always want to make sure if you're using molarity by itself in this sort of situation, that is always in liters, that volume. That will always put you probably in the right units that you're thinking you're getting and what you need probably for the calculation as well. Now, when we talk about a solution that is, for example, 1 molar, and if we have like a 1 molar solution of sodium chloride, that means that we have 1 mole of sodium chloride in enough water to make 1 liter of solution. Now, when we talk about concentration, which I think we did a little bit last time, and how molarity works is, again, if we have something like sodium chloride, it is a strong electrolyte, which means when it breaks apart in solution, it really is the sodium ions floating around and the chloride ions floating around. And again, sometimes you may not be interested in the whole thing together, but maybe you're interested in just the sodium ions that are floating around or the chloride ions that are floating around in that beaker. And again, the way molarity works, as we talked about last time, is essentially you can kind of do like a stoichiometry sort of relationship. This is a 1-to-1 relationship, which means if you are interested in the concentration of just the sodium ions by themselves in that solution, it would be 1 times 1 molar, which would give you obviously 1 molar. Same thing for the chloride. It is a 1-to-1 relationship between those two as well. And you would multiply really the concentration by 1. Not that you really need to, but you would end up with 1 molar chloride ions floating around in that particular solution. Now, again, if you have something that breaks apart a little bit differently, like you got a calcium chloride solution, that's going to again give you a calcium ion and a couple of chloride ions floating around in that solution. So unlike the sodium chloride where you get a sodium and a chloride floating around, here when you do it, you're going to get some calcium ions and a couple of those chloride ions floating around in the beaker basically. And in terms of this, if this was 1 molar, again, it is a 1-to-1 relationship between that and the calcium ions, which means the concentration of the calcium ions by themselves would be 1 molar. But when we look at the calcium chloride to the chloride, it is a 1-to-2 relationship, which means you need to actually multiply the concentration by 2, and you would get 2 times 1 molar. And that would give you a 2 molar concentration for the chloride that's floating around. It's obviously not additive. 2 and 1 don't equal 1, but it is basically the proportion. If you look at just my simple picture here, it is a 1-to-2 situation. You have twice as much chloride floating around, which means it's twice as concentrated in terms of the chloride ions as it is of the calcium ions. And that is how concentration works. I think I did the long version of that calculation for you last time, but one more time, just to show you sort of the long version of it. When we take something like 1 molar, we should get rid of the big M and turn it into moles per liter when you're doing a calculation. And this is calcium chloride, for example. We could do our 1-to-2 mole to mole relationship, just like kind of in stoichiometry. For every 1 mole of calcium chloride, you get 2 moles of the chloride ion. The moles of calcium chloride cancel. That gives you 2 moles of chloride per liter. And that is how we get to this number. So that's the long version of just multiply it by the coefficient and you'll get the same answer there. You're really doing sort of the mole to mole relationship between the whole thing and the ions when they go for a swim. Any questions on that there? So as I did here, if you're doing anything with molarity, it's a really great idea, as I mentioned last time, to get rid of that big M and show both of the units and take a more dimensional analysis approach. Again, the number will always stays with the moles part. So whatever number you got should always stay with the moles part, and it always should be 1 liter. And that's a really good way. As I mentioned last time, I think it's very common when people leave the big M in the calculation, all they think about is moles most of the time. And then again, they have no idea about the volume where it is, and they're not sure, should they be multiplying, should they be dividing? And even if there is volume there, so it's a really good idea to kind of convert it into those 2 units so that you can at least see them. So why don't we try one here? We want to know, what is the molarity of a solution that's prepared by dissolving 15.6 grams of KBr in enough water to make 1.25 liters. Some numbers from the periodic table that might be helpful: potassium 3910 and bromine 7990, I believe. Okay, so let's take a look. So obviously we're looking for molarity, which is our moles per liter. We have grams of KBr here, which is 15.6. We also have a volume of 1.25 liters. So if we just think about molarity, we already have this guy in the proper unit, so we don't have to do anything with that. But we do have to do a conversion here. We have grams and we do need to get to moles. So as I mentioned earlier, very common conversion, again, going from grams to moles. And that again is from the periodic table and the molar mass. So for KBr, we actually have one of each, so we just need to add those together, I think. So we'll do 39.10 plus 79.90. It's going to give us 119 grams per mole. And again, that comes from basically adding our molar mass from the periodic table together, since we have one K and one Br. We're going to, again, I would recommend setting up more dimensional analysis so you don't have to worry about any type of math sort of rearranging. Opposites cancel. That means we do need the grams on the bottom here, and the moles of KBr would go up on top. Remember, molar mass, just like molarity, in a sense, the number stays with the grams, and it's always 1 mole when you calculate it. And that is going to cancel the grams here. Once again, we're multiplying and dividing on the bottom there. And that's going to get us 15.6 divided by 119, 0.131 moles of KBr. That now is what I need for the top here. So I have everything I need really to calculate the molarity at this point. So the molarity would be our 0.131 moles divided by our 1.25 liters, and ends up with 0.105. Now the units here don't cancel, so you can leave them moles with the number per liter of KBr. You also can, at this point, if you like, switch back to the big M and just write big M KBr as well. So either one is acceptable, but again, in the calculation, I would use both units so you do not forget about either one. Any questions on where any of the numbers came from or anything? Take a look at another here. Maybe. There we go. What is the mass in grams of sodium nitrate that's needed to make a 2.5 liter solution that is 0.15 molar sodium nitrate? Again, some numbers that might be helpful. Sodium 2299 on the periodic table, nitrogen 1401, and oxygen there 16. All right, so we're looking for how many grams of sodium nitrate needed to make that molar. Take a look and see. So we are looking for the grams of sodium nitrate. We do have the volume, that's 2.5 liters. We also have the molarity of the solution given to us. And so definitely molarity is involved here. So if you think about molarity, which is moles per liter, and you're maybe not sure where you should start, you do have molarity given to you. You do have the volume given to you. So probably a really good idea would be to solve for moles, because once you have moles, you could then take it to grams using the molar mass, right? So again, that is how we could get to our final destination here. Now, again, if I was to do this, I would take, again, a more dimensional analysis approach. I would also get rid of this big M and say that I have 0.15 moles per liter. Again, the number stays with the moles part is per 1 liter. You could think of molarity if it's given to you as like a conversion factor. So although it is that what I just wrote, if you needed to in a dimensional analysis problem, you could just flip it upside down and use it like any other conversion factor, and it works again basically the same way. So with that being said, what I can see is I have 2.5 liters. Now I don't have to worry about rearranging this equation because I know that I just need to go opposite to cancel, and that would be this guy over here that's going to allow me to do that. And that's going to be 0.15 moles per liter. Now I'm in my dimensional analysis, so I know math, I'm multiplying, and on the bottom I'm dividing. So again, it takes the guesswork out of it if you are worried about rearranging that equation perhaps incorrectly. You could just take this more of an approach. That's going to give me 0.375 moles of sodium nitrate in this case. Now that I have the moles of sodium nitrate, I am left with basically just a conversion factor of going from moles to grams. So again, I need the molar mass to do that. So I do need to go to the periodic table and basically just add up all the parts. So here we have a sodium at 2299. We have a nitrogen at 1401 from the periodic table. And we have not one, but 3 oxygens at 16 grams per mole from the periodic table for our oxygens. That's going to give us 85 grams per mole as our molar mass. Once again, why stop with the dimensional analysis, just conversion type move? This again is going to be a useful conversion factor that you could use just like anything else, upside down, right side up, whichever way you want to use it. In this case, I could just continue on with my calculation. Once again, moles are up on top, which makes my decision making hopefully not too hard. That means I need moles on the bottom there. To cancel, that's going to give us 85 grams of sodium nitrate per mole. The moles will cancel because I am still dimensionally analyzing here and multiplying and dividing. We're going to multiply by 85. Dare I say we will end up, I'll go above it there, 31.9 grams of sodium nitrate would be needed in this case. Any questions on any of those steps there? So what does that number represent? Well, that number represents if you wanted to make the solution, you should go way out about 31.9 grams of sodium nitrate. You should add some water into it, give it a mixy, shaky. Maybe not so much shaky. And you should at that point hopefully have a 0.15 molar solution of 250 or 2.5 liters at that point now. Any questions on that? All right. Let's try another one here. So in this case, we're actually looking for the concentration of just the ions like we talked about earlier for these 2 separate solutions. So for our 1.2 molar sodium sulfate solution, what is the concentration of the molarity of the sodium ions and the molarity of the sulfate ions? And same sort of question for our 0.75 molar potassium chromate. What is the molarity of the potassium ion? And what are the molarity of the chromate ions that are floating around in that solution? All right, so take a moment there and see what you come up with in this case. Okay, so let's take a look. We'll start with the first one. So in this case, when we're interested in just the ions, we want to think about how this guy's going to break apart. And in this case, we should get a couple of sodiums floating around and a sulfate. So again, if we know the concentration of the whole thing, we basically could just multiply by the coefficient of how it breaks apart. So that is a 1 to 2 relationship between those guys. And that means that the concentration of the sodium then would be 2 times the 1.2 molar, which means for our sodium ions there, 2.4 molar would be our concentration of the sodium ions floating around. When we look at the sulfate, it is a 1 to 1 relationship, which means really we don't have to change it, but if you like, you can multiply by 1 and you should still get 1.2 molar, which would be the concentration of our sulfate. Once again, if you just kind of logically think about it, you got twice as much sodium for every 1 sulfate that goes in there for a swim, so it's twice as concentrated in terms of that ion. Question on that one there. We'll do the same sort of approach here. We want this guy and see how it breaks apart. And it is going to break apart into a couple potassium ions and a chromate ion here. And again, if we know the molarity of the whole thing, it again, in this case, a 1 to 2 relationship for our potassium. So we're going to take 2 times our 0.75 molar, which means for our potassium that's floating around in there, we got about 1.5 molar concentration. It is a 1-to-1 relationship between that and the chromate. And we would just multiply 1 times 0.75 molar, giving us 0.75 molar of our chromate floating around. We have kind of the same relationship as a 1-to-2 relationship. So again, it's twice as concentrated in this case, potassium ions floating around as it is chromate. And again, you can see that reflected in the concentration as well. Any questions on to the ion concentrations? So really the simplest and quickest way to get to it is just multiply it by the coefficient. Again, if it broke apart into like a 3 ion situation, you just multiply it by 3, 4, multiply by 4, and so forth. Any questions on that there? Oh. All right, then let's talk a little bit about dilution. And dilution is the solution. No, that's an old saying. So dilution is the process of when we take something that is more concentrated and we add more solvent. So again, a lot of cases it is water that you're adding, but it does not always has to be water, but in a lot of cases it will be. And when we add more solvent to our solution, we actually will dilute down the solution. Because we are only adding solvent, the moles of the solute before and after the dilution will remain the same. How does that affect the molarity? Well, molarity is the moles of solute divided by liters of solution, and the solution is both the solute plus the solvent, which means when we add more solvent, we're actually adding more to the bottom number, which means the bottom number increases. So when you divide a small number by a larger number, in this case, your molarity goes down. You get a smaller number, right? So a small number on top, larger number on the bottom brings the molarity down. Again, as you can see, we don't do anything with the solute. So whatever solute's in there is in there at that point. Here's a fancy way of doing that. So this is a volumetric flask, which usually means expensive. And it usually has one line right about there. And that is the volume of it. So if this was 500 milliliters, this would be like a 500 milliliter solution, usually volumetric. A couple decimal places is where you go. So you start with a little bit of water, you add your more concentrated solution to it, then you carefully bring it up to the line there and get the meniscus right there. And if you mix that up really good, you should have hopefully the concentration that you're shooting for in that solution. By the way, very common when people use a thing like this, what happens if you go over? Can you just pour out the top? You cannot, because your solute's already dissolved, and there goes your solute out the sink. And now, hoping not the sink, probably the waste container would be a better place for that. But now your concentration is not going to be correct, right? Because you got rid of some of your solute and stuff like that. So that's why you see like a little wash bottle, usually like a mezzanine dropper or something like that, to get it right to the line, because you definitely don't want to go over. Otherwise, you got to pour the whole thing out technically and start again to get it to the right concentration. So when we do a dilution, there is a dilution equation. And since pretty much molarity is the most common unit of concentration, most people roll with this equation, which is M1V1 equals M2V2. This is usually before the dilution. This is usually after the dilution. M is molarity and V is volume in each of these cases. Now, books and stuff these days like to use this equation, C1V1 equals C2V2, and C here is just generic for concentration. And that is a perfectly fine equation because technically speaking, you don't have to use molarity in that equation. You could use like percent mass to mass on each side. You could use percent volume to volume on each side. You use really any concentration unit you want on either side. And that's why a lot of times people kind of roll with the one on the right. But in practical use, most of the time you got molarity. So most people go with M1V1 equals M2V2. Now, earlier we talked about when we were using molarity and volume, that if you are not doing a dilution equation and you're not doing a dilution and you're just using molarity and volume, you should multiply or convert your volume into liters so that they properly cancel out and give you moles, which is probably what you're looking for. Once again, as I mentioned a second ago, if you take milliliters and you multiply it by molarity, you do not get moles, you get millimoles, which are, again, 1,000-fold difference than just moles by themselves. So if you're using molarity and volume by itself in a non-dilution situation, always liters. Yeah. So you always make sure the volume's in liters. Now, if you're using molarity and volume in this dilution equation, M1V1 equals M2V2, you can leave it in milliliters and it will work out okay. So if you want to do that, that's perfectly fine. Or if you want to convert to liters, you could do that as well. But it works out okay in this case. For example, if we were solving for M2, M2 would equal M1 V1 divided by V2. Basically just divide that guy to the other side. And if we just put in our units with milliliters, you would have molarity times milliliters divided by milliliters. They cancel and you're back to molarity. So it works out okay in this formula. And it also, if you did it in liters, you would just get liters at the end if you kind of solve for volume as well. So molarity by itself, volume always liters. That will give you pretty much the unit that you want, which is moles. If you're using this dilution equation, your option, if you want to leave it in milliliters on both sides, you can. Or if you want to convert to liters, you could do that as well. Any questions on that there? All right. So let's take a look at an example here. Let's say we had 19 molar sodium hydroxide. We want to know what volume of it is needed to prepare 1 liter of a 0.15 molar sodium hydroxide solution. So let's take a look at this one together. So what we really got going on here is we have a container that has 19 molar sodium hydroxide in it. And what we want to make is a new container that is 1 liter in volume. That, by the way, is 1,000 milliliters, right? And has a molarity of 0.15 molar sodium hydroxide. They are both sodium hydroxide. There's no reaction happening here other than we're doing a dilution. We know we're doing a dilution because we're starting at 19 molar and we're ending with a much lower concentration, right? So it has come down the molarity, and that means that you did a dilution. So in this particular case, we could go into our equation, M1 V1 equals M2 V2. It doesn't really matter which ones you call ones and twos, but again, usually the more concentrated is our ones, the less concentrated is our twos. So in this case, M1 would equal 19 molar. V1 we don't have. M2, which is the more dilute solution, would be 0.15 molar, and V2 would be 1 liter, or if you want to use 1,000 milliliters in this case, that's okay as well. Now, if we were going to solve for this, opposites, right? So we're going to divide our M1 to this side, and that will give me V1 equals M2 V2 divided by M1. So putting in our numbers, we end up with 0.15 molar times my 1 liter divided by my 19 molar. The molarities will cancel. And because I left my volume here in liters, I am going to get liters as my answer in this particular case. That's going to be 0.15 divided by 19. That's going to give me 0.007, and we'll call it 9. And these are liters. If I multiply it by 1,000, that is 7.9 milliliters, whichever way you want to look at it. So what does that number really represent? That number represents you would go over to your 19 molar bottle, which is more concentrated. You would take out of there, I'll just do it in milliliters, 7.9 milliliters of that 19 molar solution into your new beaker, basically, right? Now, should I add, we want a total volume here of 1 liter, which is 1,000 milliliters. Should I add 1,000 milliliters of water to that? That was kind of iffy a little bit, just so you know. Yeah. If I added 1,000 milliliters of water to this, right? How much total volume would I have in that case? 1,007.9 milliliters, but I want how much total volume? Only 1,000. So that would not be good because then I would not have the correct molarity, right? Because I added too much water. So very common dilution problems is a lot of times you'll ask like, how much water should you add to make this solution? So if you want to know how much water or solvent you need to add, typically speaking, the volume of water is equal to V2 minus V1. V2 is your final sort of volume, and V1 was like your initial of the strong guy. So if we did that, that'd be 1,000 milliliters. If I did it in milliliters, minus my 7.9 milliliters. And that would tell me that in terms of the water, I would need to put in there about 992.1 milliliters of water. So if I did that, put in there 992.1 milliliters of water, I will now have a total volume of only 1,000, which is what I'm shooting for. And now when I mix this up, perhaps a shaking as well, I will now have the correct molarity because again, I have the correct total volume. So that's a very common mistake that people make really physically when they actually do a dilution themselves, is that they go, oh, I need 1,000. So they just go, okay, I'll just dump 1,000 milliliters of water in there. But you have to remember you already put some of the strong stuff in and that takes up some volume. So you got to subtract off your total volume for how much of the more concentrated you put in there. Any questions on that one there? All right. I want you to try one here. What is the volume of water needed to prepare 500 milliliters of a 0.25 molar calcium nitrate? Okay, so let's take a look. Kind of a similar situation here. They're both calcium nitrate, different molarities, so some type of dilution happening in this situation. So again, a little M1V1 equals M2V2. Here our M1 would be usually the more concentrated one, so the higher the molarity. We do not have V1 in this case. We do have M2, which is the more dilute number, 0.25 molar, and our V2 is 500 milliliters. So once again, you got kind of like a bottle sitting here of the 5 molar calcium nitrate, and you want to end up over here with 500 milliliters of 0.25 molar. So again, we can use the dilution equation to help us figure out really in this case, when we solve for V1, how much of the strong stuff we need. So again, dividing the M1 to the other side, V1 equals M2 V2 divided by M1. Putting our numbers in, we got 0.25 molar times our 500 milliliters divided by our 5 molar. Once again, the molarities cancel. I'm going to end up in milliliters here because that's the units. 0.25 times 500 divided by 5. That gives me 25 milliliters. Is that the answer? That is not the answer. That is 25 milliliters of my calcium nitrate. That 25 milliliters is basically when we solve for V1, how much of the strong stuff we need to put in there. So we're basically going to put 25 milliliters. In this case, we're interested in how much water we need to put in there with it. So again, we're going to do our volume of water is typically V2 minus V1. So our V2 is our final volume, which is 500 milliliters. We already put in there our V1, which is 25 milliliters. That means about 475 milliliters of water needs to be added with that. And that will give us our total volume there of 500 milliliters. And again, after you mix it together, you should have a solution that has a molarity of 0.25 molar. Question on that one there. Question on dilution. So I say that's a very common sort of question, and people sometimes miss it. They'll just like circle 25. Again, how much water, how much solvent is a super sort of common sort of question. Any questions on dilutions? Okay. So let's talk about some properties of solutions here. So a semi-pyramidal membrane is a membrane that basically allows certain size molecules basically to pass through, like water, very small solute. So a semi-pyramidal membrane, although you can't necessarily see it a lot of times, it has like holes in it. And basically those holes are small enough for certain size molecules basically to pass to the other side. Larger size, there's a little out of luck there to try to get through that hole, is not going to make it. Now, when we talk about colloids, colloids are much larger than solute particles in solution. These are typically large molecules like proteins or groups of molecules or ions together. They are homogeneous mixture, which means when you look at them, they do look the same throughout. Remember, homogeneous looks the same throughout. They typically do not settle out or separate. They are small enough to pass through filters, and they are too large to get through the membranes. So they're a little too large to get through those membranes, but they are small enough to pass through filters like filter paper. If you put it into a funnel and you kind of filtered it through, it would go through. Suspensions, on the other hand, are heterogeneous mixtures. And again, they are different than solutions or colloids. They are large enough that you can see them with your naked eye. They get trapped by pretty much everything. They just kind of get stuck. They're not going to go through anything like that. For example, if you had some sand somewhere, you throw some sand on a filter paper, it's not going anywhere. You throw some sand in like a dialysis bag, it's going to come out either. It's going to get stuck because it's too large along the way. So here's those pictures here. Solutions are the circles, colloids are the triangles, and suspensions are the squares. So here we can see going through our filter paper, which also has little small holes on it. Solution and colloids can go through, but again, our suspension is going to get caught. Dialysis bag going to kind of catch everything, but really solution molecules. It's going to allow those particles basically to kind of go in and out of it. And you could test what's on the outside and the inside of the bag. Now, a process known as osmosis is when solvent molecules move from a concentration of lower concentration to a higher concentration in an effort to sort of dilute it down. So for example, if you had like a tube, wonderfully drawn here, and you got a semi-pyramidal membrane in between, and on one side you have pure water, and on the other side you got some salt water. Salt water is more concentrated because it's got salt dissolved in it. Water by itself has no osmotic pressure because it's got nothing dissolved in it. So the natural process of osmosis is going to flow from the water side, which is less concentrated, basically to the salt side, really in an effort to kind of like dilute it down. It will keep flowing until it hits what is known as osmotic pressure. That osmotic pressure is the atmospheric pressure pushing back the other way. And at that point, it will stop the flow of solvent molecules across that membrane. That is also when you do something like reverse osmosis, you apply a pressure greater than the osmotic pressure, and that forces all the water back the other way. And you get a bunch of filters right there to catch everything but the water as it goes back through. And you can kind of purify it by doing so. So osmotic pressure is basically the pressure that will stop the flow of those additional sort of solvent molecules to the other side. The osmotic pressure is related to basically how much stuff is dissolved in there. So the more stuff dissolved in it, the higher the osmotic pressure. So water, again, pure water has no osmotic pressure because it has nothing dissolved in it. You could actually calculate like the osmotic pressure in a unit that's sometimes referred to as osmolarity. And that is sometimes referred to as osmol. And you actually calculate that by taking basically I times the molarity of a solution. And what I is the number of particles there is in that solution. So for example, if I had a 2.5 molar sodium chloride solution and a 2.5 molar, bless you, calcium chloride solution, and if we wanted to figure out kind of which one would have the greater osmotic pressure, we could actually calculate something like the osmolarity. We know from our earlier conversation, hopefully sodium chloride is going to break apart into a sodium ion and a chloride ion. That is how many total ions? That is 2. Yes, so we got 1 sodium, 1 chloride. I in this case would actually equal 2 for sodium chloride. And if we have calcium chloride here, when it breaks apart, you get a calcium ion and 2 chloride ions. That's a grand total of how many ions? That's 3, 1 there and 2 there. And that would give us an I value of 3. So in this particular case, if we were to calculate the osmolarity of sodium chloride with that solution, we would take 2 times our 2.5 molar, and that's going to give us 5 osmolarity. We did it for our calcium chloride. We would take 3, which is our I value, times it by our 2.5, and it's getting late, so I'm going to punch it in. There we go, 7.5 osmolarity. The one with the greater osmotic pressure would be the calcium chloride. It has more particles that basically break apart into the solution, causing more pressure because of the presence of those particles. So it's basically related directly to the number of particles there are. So more particles probably has more osmotic pressure. You could if they both had the same concentration. If they didn't have the same concentration, then you might need to do the calculation. So for example, if you're comparing like a 2.5 molar sodium chloride and maybe like a 3.75 molar, right, calcium chloride, you would have to kind of do a little quick calculation or something. Or maybe you could still figure it out if you look at it, but yeah. Other questions on that there? All right, we will lay it up there for today.